Hi, and welcome. I imagine there are really good sessions running in parallel to this one, so thank you all for choosing that one. I'll do my best not to disappoint. It's a little bit of a bizarre setup, right? Because you're on both sides, and I'm not entirely sure who to face, so I'm going to be fidgeting a lot. Okay, so about a year and a half ago, two major things happened to me in my life. Well, one, I became a father. Thank you. Mostly to my wife, not to me. So I had a little bit of time on my hands, right? I took off some time off work, and the second thing that happened to me is I returned to programming Racket for the nth time. So no sleep, some time. I was looking for a smallish project that was not completely useless, right? Hopefully maybe web-related, even though I was not ready to buy into this whole web tech thing. So something simple. So I looked around. There's a very unscientific, well, actually very scientific estimate of mine that, say for a heavy load of ads, maybe 90%, perhaps even more, websites even today could be served perfectly fine by just a handful of CGI scripts, right? And for those of you who may not know or haven't been around, CGI, the protocol and its extensions, like FastCGI, for instance, is kind of how we attempted to do dynamic web programming around 1990s. Yeah, it's kind of RPC style. So the request comes in, your web server maps it onto the file system, runs a script from there. Whatever this spits out into the standard out is sent back to the client as a response. Now, as you can imagine, this is not cheap, right? Because if for every request you need to do all of the shebang, then, well. So FastCGI emerged as a sort of a smallish binary protocol and a simple extension to CGI in an attempt to remedy this. Yeah? So your script typically sits in the background, talking over TCP socket with your web server, and holds on to all of those external connections, things like that. Now, to my surprise, right, I couldn't find a FastCGI implementation for Racket. There are other external protocols that were implemented, but not FastCGI. What happened next, I can probably attribute either to severe baby-induced sleep deprivation or maybe brain damage, or perhaps both of them. Right? I thought, how hard would it be to implement one? Well, it turns out, not hard at all, and you don't need a fancy Lisp to do it. Unless, of course, you go off on a tangent, which is exactly what I did, and it's just a pretext, and you end up hacking a bunch of languages. Right? Something about Lisp that makes that sort of procrastination a ton of fun, and you may have experienced it. Yeah? You set out to solve a problem and proceed to language hacking, or perhaps hacking your editor if you happen to be using Emacs. Right? It sucks you in. All the while, the problem you were set out to solve in the first place kind of sits there, waiting for better time, maybe better framework, perhaps better language, right, in my case. So if we're honest, we tend to do this because it's a ton of fun, because we can, and that's exactly what we're going to do here. We'll pretend we want to implement FastCGI and then proceed to do some language hacking. Now, the typical defense is kind of, we all heard it, right? It goes something like, I'm going to implement this ultimate DSL with this particular problem domain in mind. Once I have it, I'm going to solve this problem in 2 lines of code. It'll be a thing of beauty. Right? It's a typical defense, very weak one, but it's not without merit. Like, no low-level solution will ever come close to your custom-built DSL with that problem in mind. Now, that's, of course, predicated on your ability to get the design, the architecture, even the syntax of the language just right. Right? The crux of the problem, though, is if you think programming is hard, and I tend to think that programming is not easy, design is that much harder. Just think about the last time you had to fight a very broken API. And it's not like you can well, you can't blame the author, obviously, but it's not like they had this malicious intent to ship this broken thing. It's just that getting it right is difficult. You're designing. So why is it so hard, especially when you design a language or you design an open system, you haven't built, you haven't seen anything like that before? Why? Why is it so difficult, especially if it's meant to be extensible? So I implemented a bunch of languages in DSLs, both in Racket and in Clojure, and it got me thinking this time around, like, why is it difficult? Typical approaches when you design something like this is either bottom-up or top-down, and in my experience, bottom-up is perhaps the most practiced technique, for good reason, right? You start very small, manageable pieces. Your feedback loop is rather tight. You can even go systematically about it if you subscribe to test-driven development, right? Then, so the way you start to implement things is you zoom in to the parts and you implement the pieces that you can actually conceive and make them compile and run. So very often you just cobble together a bunch of stuff that's already available as external dependencies, right? Things like that. The problem, of course, is when you zoom out and you start to implement the rest of the system. You haven't seen the system, but something is already running. Your tests are green, so great. Yeah, but the problem is those external dependencies, they kind of force you into a certain design already because they provide API. You have to use that API. You haven't played with any of it, but you have those building blocks. Your system compiles, tests are green, you're happy. So you proceed as if nothing happened. That means bottom-up kind of forces you into a design. Whether it's a good design or bad design, who knows? But it somehow works out in the end, most of the time. That is, another way of putting it is, I'd say bottom-up kind of, it precludes, you can't really let your imagination run wild, right? Take the wheel a little bit, play around with the system. It's not that kind of thing. So at this point, most people would go bottom-up pretty much every time, right? And I can't really fault them because programming has us deal with so many unknowns that it's perfectly fine to seek solace wherever you can get it. Like it compiles, your tests are green, what's not to like? I noticed that at least when I Racket the language, I tend to go, if I'm designing a language or work on something that's not small and I haven't worked before, I tend to go the other way around, top-down. Now, what do I mean by that? I imagine that I have a language already in place. I sit down, I start typing, I start writing, playing with the whole system. Now, obviously, I don't have that language on my machine. It doesn't run. There's nothing on my machine. But I do have it in my head, some approximation of it, surely, right? Because I have it, I can play with it. It's actually, so I would say that this approach is almost an act of writing. You sit down, you write the pen and paper style, but with a laptop and a bunch of other constraints. Now, I keep saying top-down, but really I encountered this kind of technique, and I'm going to call it technique, very early in my programming days. How many people recognize where this is coming from? All right, how many? Not many. SICP lectures, right? Available on YouTube. If you haven't watched them, you're in for a treat. It's good enough for Abelson and Sussman. What they called, well, what I call top-down, and we tend to call top-down, they called wishful thinking. Yeah, in Racket, it would be hashline wishful thinking or something like that, right? So the essence of what they suggested, I think, as wishful thinking is pretend you have it all. Pretend you have semantics, syntax, all the building blocks you need, and proceed with an attempt of implementing your system as if you have all of it, and hope that it somehow is going to work out. Now, trouble is, our languages are kind of ill-prepared for that sort of thing. Yeah, we are supposed to use what minimal building blocks they provide, means of combination and abstraction, for any problem, no matter the problem. You can employ this technique in the small so long as you are happy with those building blocks. It doesn't help that I'd say most people are a little bit unprepared to not having a running system, not having it compile, no tests, right? It's scary. So like I said, top-down kind of calls for an act of writing. And the reason we can do this in some Lisps, I'm not going to say in all Lisps, because macro system, well, maybe in all Lisps actually, because there is a macro system that kind of has your back every time. I think this is no surprise that this should come up in the context of Scheme, right? Where you have a powerful macro system that kind of has your back every time, in that you can macro any idea into submission. It doesn't validate your idea, right? But it sure is an omnipotent tool to have in your toolbox. It lets you, I think it lets you play a little bit, like loosen your grip, like shake off the constraints that language puts on you. So some Lisps can help. They provide you with a bunch of tools right out of the box. Like for instance, you can count on having a reader. So you don't have to parse as hard, as long as you're happy staying in the S-expression land, which I'm content with. If you're lucky, maybe they even parse into rich syntax objects, not just lists. They give you a decent enough macro system, maybe even hygienic one by default. And they work as long as you're on the happy path. What do I mean by the happy path? The experience of using the end result that you produce. The language or the DSL, the extension to a language, something like this, right? Because, and it's a gnarly problem, because when your homegrown DSL blows up, as it inevitably will, it will be in your user's face. Like chances are, in your garden variety Lisp, I'll be staring at a wall of code I've never written, with very few tools at my disposal to help me on the path of resolving this. Now, there are other Lisps that are perhaps more demanding on you as the implementer, but they make more ambitious macros possible, and therefore more ambitious DSLs possible, and at the same time, hopefully, the result more habitable. Yeah? So perhaps in addition to all these things, they give you, let's say, macros that communicate, actual hooks into the compiler, languages that can coexist, call each other, cooperate, right? Maybe even the entire platform built with multilingual ecosystem in mind. So this is the ambitious part. The habitable part is, well, maybe at the very minimum, they ensure that there is enough context implicitly received or explicitly defined by you, specified by you. At the very minimum, they lift the error messages to your homegrown language, so your user doesn't get lost. Now, Racket is one such language. It's probably not the only one. But to the best of my knowledge, it's probably one of the rare ones that push those metaprogramming ideas the farthest. And in this talk, we shall speak Racket. If you don't know it, don't fret. As long as you're comfortable looking at a little bit of Lisp on the screen, you should be OK. I want to, through an example, show you some basic glimpse at some basic ideas that are still quite powerful in Racket. OK, so how many of you actually know Racket? A few, OK. How many of you have heard about Racket? Oh, good, nice. All right, you haven't. OK, great. Well, let me give my very idiosyncratic take on Racket. And I'm sure a lot of Racketeers will disagree, but this is mine. I'm taking the stage, I can do it. All right, I'm not going to go all Wikipedia style on you. Yeah, it's multi-paradigm. Yeah, you can bring any paradigm you want. It already has a lot of them. And I'm not even going to quote the founding fathers of Racket. It is a programming language. But without any context or first-hand experience, this sounds really cool and delightful, but kind of vague. And if this sort of thing makes you curious, I implore you to seek out and read the so-called Racket Manifesto. You can even watch Matthias Felleisen, the father of Racket, talk about it online on YouTube. It's a different kind of manifesto, not your typical one, in that it's not so much a declaration of intent or call to arms. It's like I'd say 30 plus years of experience building Racket and its ecosystem distilled into one text. It's a good read. Now, as far as I'm concerned, here's one defining feature of Racket. Pick a language, any language, and show me some feature you really like. Chances are I can steal it. I can steal it, I can bring it to Racket, perhaps, even likely, improve on it. In fact, other languages will make appearance in this talk. Lua, Clojure prominently. I'll even mention Erlang as source of inspiration. I myself happen to be a Clojure programmer. This is where the money comes from. But Racket is my first love. This is, in fact, the language that I used to teach myself programming back in the day. So I keep returning to it, and every time I do, it's from somewhere else, so I bring those ideas that I liked to the language, and the macro kind of has my back. Clojure programmers in the audience? Okay, way more than Racketeers. Good. I'm going to lean a little bit on that knowledge. In my opinion, Clojure is kind of what happens when you decide to tackle this really gnarly problem, enterprise programming, and you succeed. It's a cool language. I really like it. It's very pragmatic. It comes with some very tasteful defaults. Ergonomics is great. Data is front and center. Platform gives you a lot of batteries out of the box, battle-tested batteries. Unfortunately, platform is also what limits it, I think. Now, Racket is what happens when you decide to build the second best language in the world and succeed. There is a punchline here. I'm quoting Matthias Felleisen, by the way. The punchline goes something like this. Chances are the best language in the world will be built in Racket. Think about what this implies, because this will inform your design, the features that make it into the language. You are setting out to build the ultimate platform for building DSLs, right? So necessarily, metaprogramming becomes front and center. It's not the only feature of the language, obviously, but that's what it makes it possible. Now, there are two interesting features that made it, I believe, into the language from probably from day one: pedagogy and research. Now, I'm but a humble consumer of research. I read papers, I sometimes implement them, but now that I'm a father, suddenly pedagogy matters a whole lot more. I'm happy it's there. Now, languages are prominent, of course, in Racket. Like every snippet on the screen is some kind of language, essentially, right? So think of it as a separate file that uses a very different language compared to everything else, right? If the end users of your language either don't care for params or hate them, you can go without if you don't want to. Now, as far as full-on languages go, it's all in this first line, right? That starts with #lang. Now, with it, you provide both the reader and the expander for what follows. What do I mean by the reader? How the hell am I supposed to read this thing that follows? Really. Expander is the meaning of what I just read. What's the semantics of all those identifiers that I just encountered? That's about it. That's not to say that Racket is not big on embedded DSLs that work, small DSLs that work at expression level, at form level, right? In fact, they're pervasive. They're everywhere in Racket. That first line is a DSL, and a user extensible one at that. Racket requires the way you import, export stuff, right? Loops, comprehensions, beautiful Racket pattern matching facility with Racket Match. All DSLs, all user extensible. Now, practically speaking, here's what I think makes metaprogramming in Racket special. Like, it takes its roots in schemes, so all the usual suspects are there. Compiler deals with rich syntax objects that track a bunch of stuff, location obviously, but also compiler is aware of bindings. So scopes are explicit, it keeps track of those scopes. In fact, you can slice and dice them. You can take this context, borrow it from one place, slap it somewhere else, talk about breaking hygiene systematically. Stages of compilation are explicit, very often spelled out. That means metaprogramming sort of to the nth power possible, at least feasible. If you head over to Racket website, specifically to documentation, very surprisingly, quite inconspicuously there somewhere, there's a link to syntax metaprogramming helpers. This is where the real power is. Like, it will teach you all about syntax parse framework, syntax classes, that sort of thing. And in a typical Racket fashion, it's just a language. This is a sort of a glimpse of it. I'm not going to teach you this framework. So all I do here is define a bunch of syntax classes, like hold there, which I'm going to use down below in the actual macro, this threading lambda thing. Now, what are those syntax classes? Well, they take a bunch of parameters. They take a bunch of patterns that I specify. And those help compiler decide how to parse whatever is happening in the macro and enrich it with some context that I can explicitly extract and provide, or it implicitly enriches the result of reading with that context. That becomes really powerful. That is to say that in Racket, very often you start writing your macros in DSLs by extending the language for writing macros in DSLs. So in Racket, it is kind of turtles all the way somewhere. So I gave you a little bit of a backstory and then completely go off on a tangent, obviously, right? We talked about the top-down approach, so a bit of philosophy there, some metaprogramming stuff. I even mentioned, I promised you I'd mention closure. I mentioned closure. I'll probably mention it a little more. We'll see. So let's actually do something, right? Let's start implementing FastCGI. So it's a small spec. It hasn't changed since 1996. It's a binary protocol. It was meant to be extensible, but unlikely, right, at this point. So there are two problems we need to solve. One, since it's a binary protocol, we're on the wire, we need to parse and pack those bytes. Yeah? The second problem, actually modeling the protocol, we need to, well, program it, right? So let's solve the first one, the parsing bit and packing bit. So it is a sequence of bytes. You start by parsing FastCGI header. It will tell you, one of the bytes will tell you what type of a message you're looking at, and you proceed parsing it accordingly, right? It becomes a little more involved because parameters of the request are passed on the same wire. They encoded as name-value pairs, and they were trying to save bandwidth, so they thought it would be a good idea to encode them as 1 byte or 4 bytes. The way you decide which it is by looking at the most significant bit, right? How do you normally approach that sort of thing? What do we normally do? Something like that, right? You go bitwise arithmetic, shifting, adding, ORing, soaring, masking, that fun stuff, cryptic values with X before them. Like, what the hell are those? Feast your eyes on this. Is it good code, bad code? Aesthetically, is it pleasing? The moment I wrote this, I thought, I'm parsing name-value pairs that I mentioned. The moment I wrote this, I thought something's off. Okay, it is a programming language. You could be writing Python or C in it, but that's what you end up with. The larger problem is not that it doesn't have error checking there. It doesn't, I promise. It's that, and it's just part of the code. The bigger problem for me is that this is not what I have in my head at all. I don't think in bitwise arithmetic. Maybe after years in C-land doing some systems programming, re-implementing TCP stack, I would. I don't. I have boxes with zeros and ones, and I match on them, right? There's some patterns in my head that I'm going to use. So briefly, I actually considered, and I sat down and I sketched out how I would write a pattern matching facility, a language of bit patterns. But then found out that someone beat me to it, and honestly, I couldn't be happier because I suck at bit twiddling. I mean, I can do it, but I would have to get a refresher. So a very prominent racketeer, Tony Garnick-Jones, looked around, and that will be a theme of this talk. He looked around and racketeered one from Erlang. He reimagined it as this beautiful library called bit syntax. That's all it takes to parse and pack FastCGI headers. That's all it takes to parse parameters. Now, there is one thing that stands out, which is obviously not part of bit syntax, that FCGI length there. That's a pattern, a custom pattern, so my extension to the language. It's just a matter of writing a small macro whose essence is in these two cases. I told you, you need to look at the most significant bit. Look at that very first pattern. It's kind of obvious what I'm doing. This is the scheme way, the Racket way. So, of course, it's a programming language. You can write anything you want in it, but please don't write Python or something. That said, I have to caveat this, right? FastCGI being very simple protocol, it doesn't warrant this amount of work, right? But if you are tasked with re-implementing TCP stack, you may as well take your time. OK, let's zoom out a little bit. Time to model the protocol itself. Now, this being a protocol with an actual spec that's unlikely to ever be extended, wishful thinking is nice and all, but it works well for designing a language or an open system, let's face it. So it doesn't really warrant this sort of approach. But so I went with a mix. I leaned a little bit on my very rough at the time understanding of Racket structs and the simple inheritance model that they provide and Racket generics. Yeah? So what I did, I sat down and I sketched out the entire system, having made some simple assumptions about how inheritance works and all that sort of things. It was beautiful and very extensible, even though protocol will never be extended, because why not? I was having fun. And then I zoomed in and started implementing smaller pieces using Racket structs and relying on generics. And the entire system starts to come undone. Like my beautiful sketch very quickly turned into this Franken monster. Why? Is it the wishful thinking thing? I think the problem was those constraints were too severe. For the sketch that I designed, for the design in my head, they were too severe. But it wasn't a total waste because it kind of hinted at what I wish I had. And what I wish I had was a kind of a more nimble data type that would let me sketch and prototype quickly, that would afford more generously those inheritance patterns that I had in my head, right? That sort of thing. What does it mean? Time to go racketeering. Now, I was playing with this nifty little language at the time called Lua. Some ideas are very good. In particular, the idea of metatables stood out in this context. What are metatables? Metatables is what happens when you want prototypes and prototype inheritance, but happily you are not JavaScript. It's pretty good, actually. Now, I decided, hey, I'm going to enrich Racket, not implement tables, but enrich the language with tables. So what's a table? Table is, how many people know Lua tables? A few, very few. All right, so what's a table? It's an associative data structure. Think keys, values, hash maps, hash tables, that sort of thing, right? But it also provides means of indirection, like prototypes would, right? So every table would have a metatable. What's a metatable? It's just a table. So a simple example, the simplest example would be, what do you do when the key is missing? You look something up, it's not there. Well, the metatable will decide what to do. Yeah, that sort of thing. So here is a very prototypical, pun intended, example with different types of bank accounts. right? So we define an account or a table that's going to be a metatable for accounts. That every account will start with a balance of 0. We define a bunch of methods, what those are. Those are just procedural values that happen to be on the table. We just add them there, but there's a fancy syntax to do that for a metatable. And once we have our prototype inheritance going, which with Lua semantics would take like 2 or 3 lines of code, then we can proceed with more ambitious accounts, like limited account, then add money, withdraw money, check the balance, and it would work for all of those types. Yeah, that sort of thing. So prototype inheritance going. Now, why I'm showing you this? Because the way I approached doing this, I had a couple of examples in my head. Some I took from Lua book, right? I sat down. I didn't have the language. I just started writing. Something like this. I had an idea of semantics in my head. So the tables are created with curly braces, which is no surprise for Clojure people, but curlies are not special in Racket, so we have to work a little bit to take them back. Colon balance, a keyword-like thing. Also, keywords are special in Racket, unlike in Clojure. They're not, well, they are self-evaluated, but they're not allowed in expression position, so we need to do something about that. That define is obviously somehow aware of table notation and semantics, like that sort of thing. We use colon, colon, colon notation in different flavors to call those methods and all of that stuff. How does that work? They're part of the identifier. By the way, the difference between colon and colon, colon is that colon, colon just sends implicitly the receiver as the first argument. That's all. Once you have prototypes going, you can become very ambitious. And I don't expect you to read this. This is how Lua people would implement multiple inheritance. I was dissatisfied with this example because it's closed and it's opaque, and that you can't add and remove metatables. Right? And that led me to a very different semantics. So my first implementation actually took maybe 200 or 300 lines of code, just a bunch of macros, and I had my Lua going completely for me with all of this fancy syntax. But I changed the semantics since, and all the magic lives in just these 3 meta methods. There are some more. What are meta methods? They're just methods or procedures that happen to be, or tables that happen to be on a meta table, and some names are treated specially, some keys are treated specially. Right? Get, when it's there, decides what to do when the key is missing. Set, when it's there, decides what to do when the table changes somehow, like you add a key, remove a key, that sort of thing. Set meta is only ever called once, if it's present, as the final step of the constructor that lets you like change the instance you create somehow. So that sort of thing. And you can change those in any way you like. Another design decision I made early on is I prohibit undefined as the value. And the entire infrastructure works seamlessly to ensure that this invariant holds. Right? Because you very quickly run into a question, OK, how do I signal that something isn't there? OK. Kind of pushing it. So depending on your answer, I may skip this section, although it is an interesting design. Symbols, quoted symbols, keywords. Who knows what I'm talking about? OK, enough people. I'll introduce you to an interesting sort of design of Racket, and it allows for really powerful tricks. So symbols are really overloaded in Scheme and therefore in Racket. Yeah, we use them for everything. Clojure made a very good decision of introducing keywords as self-evaluating data type. Now we use keywords for everything. Racket made a different decision. Its keyword starts with #, by the way. They are not allowed in expression position. It sounds limiting, but really I came to appreciate this decision because it makes certain tasks much easier. The thing is, I didn't want to choose. I want both. So I implemented tags. Identifiers that start with a colon, like keywords in Common Lisp or Emacs Lisp, right? Or maybe Clojure. All it took to do that is this amount of code. I don't expect you to understand it, but this is where I'm going to describe a design decision in Racket. It's pretty cool. So a compiler will expand certain forms into intermediate forms that start with #%, like #top in this case, right? So for instance, a procedure application will be always expanded into intermediate form starting with #% app. Why is this cool? When you have an unsolvable computer science problem, what do you do? No, seriously, I'm asking a question. That's right. If that doesn't solve it, you don't have enough levels of indirection, right? This is kind of what they did there. The thing is, compiler will continue to expand this form, but it will look up the binding or the meaning for that form at the call site, meaning I can provide my own semantics. You can provide your own semantics, right? And that's our clue, because unbound, I told you earlier, compiler tracks those bindings, right? So unbound identifiers get wrapped into this #top thing, and we can take it over. That's all it takes to implement tags. It's kind of a hack. All right, so let's talk very quickly ergonomics. Yeah, curly braces to construct tables. We allow identifiers in the app position. If it's a table, it'll be used as a meta table. If it's a procedure, it'll be called on the instance being created. There's an experiment of mine, there's #check followed by something. It's like a lightweight syntax for traits or mix-ins right there in the constructor. And I'll show you why I wanted this. We also ricketeer from Racket. Those intermediate forms are cool. So we expand constructor into this intermediate form #table, which you can overtake. So you don't have to rely on me implementing some semantics that you want of a constructor. You can change it completely. And these are all the flavors of invoking methods on the table or procedural values and stuff like this. Yeah? And the way you implement this actually is a bunch of macros that just leverage #top and #app. This trick works for this as well, very well. We also expand these into yet another intermediate form, #:, which you can overtake. If you like your closure semantics of looking stuff up, go ahead and implement it. I won't object. I don't like it, but define is a drop-in replacement for Racket define. But it's aware of all those table notation, of all that table notation. It's very convenient to implement a bunch of methods on a meta table. We extend the Racket match, so you can pattern match on tables, obviously. How do we provide all of this? Unsurprisingly, as a language, Racket with tables. Racket with tables at the top, and you have that language. Now, this is actually something subtle, but very magical. Because essentially what just happened is I reprovided all of Racket. You have all of Racket, but augmented with this interesting feature. The language itself is richer for it, but they coexist. And this is made possible by the multi-collection packages that Racket provides. It's actually really fancy. It's really good. All right, some interesting examples of metatables. I promised you multiple inheritance. Here's one. It's a possible implementation of multiple inheritance. That's all it takes, just one meta method. It's not the only one, but it's open in that you can add metatables, you can remove metatables. We recover the identity a little bit. What exactly it means that you are of this type or not, it's up to you to decide, but you can decide it and then implement your own semantics. I decided, Isa will reply, hey, do I have this meta table somewhere in my chain or not? Something like this. OK, spec. Nothing to do with closure spec, maybe superficially, right? It's a good idea to declare what slots can appear on a table. You do this on the meta table. And that's why I wanted this lightweight syntax for traits. It comes in really handy to do things like that. Spec itself will not check those invariants. But we derive two more meta tables. Open spec and close spec, these will enforce the contract anytime the table changes. Finally, so tables are actually callable. They already double as procedures. And what exactly this means, you get to define yourself by implementing a proc meta method. You don't have to ask me, just do it yourself. If you like what closure is doing, you can do that. Racket stole a really cool concurrency model from concurrent-ML. It's beautiful with synchronizable events and threads and all of that. And I wanted for you to be able to use tables as synchronizable events and for you to actually customize and decide what exactly this means to synchronize on a table. So all it takes to implement this is one place where you need to sort of drop down to Racket is to define another table-like struct type. But then the rest of the ecosystem works seamlessly with that type of table. That is to say that tables are kind of not just first class, they're Racket first class. They're aware of the largest ecosystem, which I think is OK. As you can imagine, by that time, I kind of ran out of steam, right? Remember we started by implementing FastCGI? Have we actually implemented it? Well, yeah. I mean, it's not going to win any prizes. It was almost an afterthought at this point. I kind of got exhausted. But I have been running a FastCGI application this entire talk. It's in my hand. It's this clicker right here. It's just a web page that talks to my FastCGI backend written in Racket, and that talks to my Emacs, and drives the presentation, and grabs prompts and sends them back to my iPhone. That's kind of what I did. Now, obviously, it wasn't my intention to build it, but I wanted to show it off, right? So where wishful thinking kind of approach would work best, and this is actually what I wanted to build in the first place, would be something like a hash lang for writing FastCGI scripts quickly, right? So implementing a hash lang PHP is no problem at all. It's not difficult at all, right? But something cleverer than this, I think, is possible, and I just don't have the time to keep working on that. How are we doing for time? All right, so I'm going to wrap up here. There's some stuff that I've been kind of thinking about and working a little bit on, like immutability, which should be easy to implement, dispatch, all things dispatch, predicate dispatch, because tables are really cool for that, I think. If this sort of thing interests you, come talk to me. And I guess I'm going to leave you with this. It's actually a valid, viable strategy in a language like Racket. If you're out of ideas, actually, even if you're thinking about building something, stop, look around. Thank you.